About graphs of y equals cosine x and secant x, and we're also going to talk about something called a damped sine and cosine function, which we're going to do with our graphing calculator. So if I want to graph y equals cosecant of x, one way I could do it is by plotting a bunch of points. That would be kind of the longest way to do it, but I want to show you kind of where it comes from, so you kind of have some understanding of it. And so y equals cosecant, I'm not very good at knowing the values on the unit circle of cosecant, but I am pretty good at knowing the values of sine, right? And you guys are probably pretty good at that too already. So to graph y equals cosecant of x, what trig function could I graph instead? 1 over sine of x, right? And so if I'm plotting points and I want to plot the points, say from 0 to 2 pi, so say this is pi over here, 2 pi, and we'll put a pi over 4, pi over 2, and then a 3 pi over 2 there. When sine is 0, what's cosecant? Or when sine is, what's the sine of 0 radians? What's the sine of 0 radians? 0. No, it's y over x, right? So it's 0 over 1, which is 0. What's the reciprocal of 0? Undefined. It's infinite, okay? So what happens right here is you have some point that's way, 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 way up there, right? Which we'll talk about in a minute, okay? So what if I went to the cosecant of pi over 6? Cosecant of pi over 6. What's the sine of pi over 6? 1/2. So what's the cosecant? Reciprocal of 1/2 is 2. Okay, so if this is 1, I would get a point up here at pi over 6, which is 1/3 of the way to pi over 2, right? At 2. All right? And up here, we'll talk about that one. How about at pi over 4? What's the cosecant of pi over 4? Approximately. Okay?
It's about 2 squared root 2 over 2.
Well, the sine of pi over 4 is root of 2 over 2. The reciprocal of that, after you simplify it, is root of 2. Okay? Root of 2. Okay, so it's about 1.414 if you, okay? So at pi over 4, we're at about 1.4, okay? When I get to cosecant of pi over 3, that I think is 2 root 3 over 3. Is that what it was? 2 root 3 over 3? Yeah, when I simplify it, it's a reciprocal of root of 3 over 2. So it's 2 root 3 over 3.
What's the cosecant
of 2. Okay. So this is 2 root 3 over 3. I learned in high school that this is 1.732. 2 times 7, 1.32 is 3.4. 3.4 divided by 3 is about 1.1. That's why you rationalize denominators. Because back when I was in high school, we didn't get to use calculators, and you could figure out in your head kind of what cosecant of pi over 3 was. So I'm guessing that the cosecant of pi over 3 is about 1.1, right? About 1.1 or something like that. So that's like 2/3 of the way. So we're at about 1.1. What's the cosecant of pi over 2? Cosecant of pi over 2 is 1, right? Because the sine of pi over 2 is 1, and the reciprocal of 1 is 1. What's going to happen over on this side? What happens to sine as I pass pi over 2 on my unit circles?
It goes down.
It goes down, so this is going to go up, except what sine is still going to be positive, right? You're right. So it's going to start going up again like this, okay? And over here it's undefined, so it's going to get really, 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 because these numbers, sine gets really, really small as they get closer to 0, so the reciprocal of sine gets really, really, really big. So what you end up having as you get close to pi and close to 0 is you have, what are those things called? Those, very good. You have those lines that they get close to, but they never touch. I have to stand in your way for a minute, okay? You have an asymptote there, and you have an asymptote here. And so what happens with y equals cosecant of x is you get a curve that looks kind of like this, going down like this. And then when I get into the third and fourth quadrant, what's true with sine in the third and fourth quadrants?
Negative.
It's negative. So cosecant, which is a reciprocal, is also going to be what? Negative, right? So if I put a -1 here, a -2 here, what I get is a curve looking kind of like this, going up and down like that, and it repeats itself forever and ever. Now, an easier way to graph this, which I'm going to show you in a minute, is to actually graph the sine function. So I'm going to change colors to nice teal, and sine goes up like this, and down like this, and down like this, and up. What? Oh, I missed. Oh well, you get the idea. Up like that, and down, and it goes like that for never and ever and ever, right? You get the idea, okay? And everywhere I have a 0 on my sine function, what do I have on my cosecant function? An asymptote. Everywhere I have a 1 or a -1 on my sine function, what do I have on my cosecant function? A 1 or -1. Same thing, right? Because the reciprocal 1 is -1. Everywhere the value gets really, really small, this value gets really, really big, right? Because the reciprocal of a small number is a big number, right? A number less than 1 is a number bigger than 1. And that's why, so the easiest way really to graph a cosecant function is just graph the related sine function, sketch it in, draw in your asymptotes, and then everywhere there's a maximum or a minimum, that's where you have a vertex of your cosecant function. Yes, Emily? Yeah, in this case it'd just be y equals sine of x, but we'll do some ones where there's like shifts or stretches or something. Okay, so in general, domain of y equals cosecant of x, you would just write that x is not equal to everywhere there's a pi. So at pi plus n pi, right? Domain x is not equal to pi plus n pi, which means any multiple of pi, including 0, right? If I put a 0, if this is an integer, right? Pi plus 0 plus -1 would be, that's the way I would write it. The, what else? The domain is let's just talk about the asymptotes. Asymptotes are exactly the same, except instead of having a not equal sign, I have an equal sign, right? Plus n times pi. And the range is, I guess I should have 2 dots there. And the range is y is greater than or equal to something. What? What's y always going to be greater than? 1. And y is less than or equal to -1. Okay? So that's the range. And then the period is the same as with sine. So the period is, what's the period of sine? 2 pi. And that's all there is to it. Okay? So this cosecant function, if I were going to continue to graph it, right, I put in an asymptote here, okay? And then I'd graph it another, whoops, you get what I mean, okay? I'm doing bad graphs now because I'm right. Okay? Questions? Can I move on to the next thing? Okay. Next thing is y equals secant of x, which is very, very similar. What's secant related to? Yeah, so secant of x is equal to 1 over cosine of x. Yes? And so I'm not going to go through that whole process of finding numbers and all that. I don't want a dotted line. I want a solid line. Okay? Let's make it solid. And all you really have to do is graph cosine of x, right?
Oh, and then you
And then you, so I'm just going to show you, here's cosine of x, we'll call this 1, and this 1, -1, and here is pi, and here is 2 pi, and here is, here's pi over 2 over here, and 3 pi over 2, and it goes in the negative direction as well, to negative pi over 2. Let's just go backwards this way. Pi, negative 3 pi over 2, negative 2 pi over there. And then I'm going to graph y equals cosine of x, which starts where?
1.
It starts at 0, 1, right? And so first thing I'm going to do is graph y equals cosine of x. And it has a 0 at pi over 2. It has a minimum at -1 over here. And then it goes back up through this point. And it goes back up here to 2, 1. I'm going to try to graph it in different colors. So cosine of x looks something like this. And we talked about it being an even function. So it is symmetrical, symmetric, right? About the, oh, that's bad. Symmetric about the y-axis. And so just like I have with sine, it has an asymptote everywhere that cosine has a 0. Okay, so if I draw asymptote there, asymptote here, asymptote here, asymptote here, okay, should go through this point right here, not. And now I'm going to graph in my cosecant function. In what color? How about black? Or whatever color that is. Do you guys understand what I meant? And so everywhere there's a 1, the reciprocal 1 is 1, and everywhere this cosine gets small, secant gets big. All right? Okay. Like that. And then like that. And forever after. Now it's perfectly okay if when you're graphing these, that's the way I do it, that if you leave in the cosine function, okay? You don't have, maybe you want to make it a dotted line or something and make the secant function a solid line. Who had a question? Who said they don't understand?
How do you find the domain stuff again?
So domain is like what are the x values it's allowed to be, right? So what is it not allowed to be? Because it can be everything except where there's asymptotes, right? And so what's the domain? X is not equal to what? And the asymptotes are at multiples of what? Pi over 2. So pi halves plus n pi, where n is a positive or negative whole number, right? Integer, okay? The asymptotes, like in the last problem, asymptotes, x is equal to this, right? Pi over 2 plus n pi. The range is exactly the same as it was for the last thing, for cosecant. So the range is y is greater than or equal to 1. Well, how do you do that? Union? Yeah, or let's just write, or y is less than or equal to -1. When we're doing the inverse functions, this will make more sense. So it always has to be bigger than 1 or less than -1. Because sine is always between +1 and negative.
Is it the same phase shift and stuff?
Yeah, it's same, the period. And again, the period is 2 pi, just like it is for sine. So, okay, so we'll do one now. Allie,
Yes.
time to wake up.
I know, I'm so tired. I'm listening. I have notes.
It's okay. That's a pretty picture, I gotta say. All right,
Yeah, it is nice.
so thank you. So then we're gonna do one where it's not just plain old sine. Can I erase this? Can I move on? Okay. So if I have y equals 2. So if they say graph by hand, which we will, me and Mr. Beamer will say this to you. And so we'll say graph 2 periods of y equals 2 cosecant of x plus pi over 4 by hand. Okay? So the way I would do that is just by starting by graphing y equals 2 sine of x plus pi over 4. Okay? Which is pretty easy, and then you could figure it out. So what's the period of this function? Period of y equals sine of x plus pi over 2 pi. Since there's nothing in front, right? That means there's a 1 there. So 2 pi divided by 1 is 2 pi. So this is the period of 2 pi. What's the shift, the phase shift? Okay? It's pi over 4 divided by 1, but since this is positive, the shift is very good, Sam. Shift is pi over 4 to the left, okay? Or negative pi over 4, right? So that's where it's going to start. And we'll worry about the endpoint in a second, so I'm just going to draw a graph with solid lines. There we go. Solid lines, I don't like that color. This color. So here we go. Here we go. God bless you. Okay, so my start point is going to be negative pi over 4. Who can tell me what my end point is? What's my end point? Where would it end?
2 pi.
Very good. Which one?
Or the last one would be negative 2 pi.
Well, let's go this way.
Or that one would be 1 and 3/4 pi.
Yeah, 1 and 3/4. So just take negative pi over 4 and add 2 pi to it. Well, 2 pi can be written as 8 pi's over 4, right? So if I add 8 pi's over 4 to negative pi's over 4, how many pi's over 4 does that give you? 7 pi's over 4, right? So my endpoint, that's the way I do it, which seems to be the quickest way. So I have negative 7 pi's over 4. So that's the start point, that's the end point. Probably what you want to do is find this middle, okay? Well, I take the average of those two. What's negative pi plus 7 pi?
6 pi.
6 pi over 4. What's half of 6 pi over 4?
3 pi.
3 pi's over 4. You just divide the top, okay? So this is going to be 3 pi's over 4. The halfway between the halfway is going to be 1 pi over 4. And the halfway between here is going to be how many pi's over 4? What's halfway between 3 pi and 7 pi? How many pi's over 4? 5 pi's over 4, right? And then I am going to graph this sine function. How high is that sine function going to go? 2. To 2, okay? And it's going to go down to negative 2, right? And so you got to give yourself, unlike I did, enough room to graph the trig function. So it's going to start here. At the quarter point, it's going to go up to a maximum, right? At 2. At the halfway point, it's going to go back to 0. At the 3/4 point, it's going to go back here to negative 2. This is negative 2 right there, right? And then it's going to go back up here. So I'm graphing first. Whoops. Yeah, that's right? So I'm going to first graph the sine function. Let's do it with a dotted line. Okay, so first I'm going to graph the sine function, which looks like this, right? And keep going forever. Mine's not very, something's wrong. What's wrong? No, that's right?
That's right.
Right, it's just my scale is kind of squished or wrong. And then draw an asymptotes everywhere that you see a 0. Okay, so I'm going to draw an asymptote in here. I'm going to draw an asymptote in here. And draw an asymptote down. Oh, I didn't draw enough periods of it. Okay, but you get the idea. As long as you label like 1 or 2 periods of it. And whoops, another asymptote. This should cross right there. I messed up. Then it goes through that point right there. And now I can graph my actual cosecant function with a solid line. And we'll make it thick. So here it is. Whoa. So there it is. And there it is. You could do a better job. But okay. And then you could go on forever. This one goes down here, right? And the next one goes up here, and so on and so forth. As long as you show me that you know what you're doing in here, that'd be okay. Okay? Questions about that? Easy? Okay. Sorry, I got to teach so much, but there's one more thing. Okay? And this is going to be kind of fun. The next thing is called a, I don't want this fat line. Damn. Ooh, that looks cool. We're going to do a damped sine function. So if I, so you see these kind of things when you have a, say you have a spring, right? And I have a weight on the end of my spring. And I pull my weight down and I let it go. What's going to happen to my spring over time?
It'll get stretched.
It'll get stretched, and it will, if I'm graphing the displacement of that weight over time, you understand it's kind of going to do that?
Yeah.
Because of kinetic energy or whatever that physics stuff is called or something like that. So it's going to bounce up and down, and after a while, it's going to come to a stop. So this, turns out, can be modeled by a trig function, Doug, and other types of functions. So this particular one we'll talk about in a second, but if I want to graph, like one way you can do that is by putting a number in front of the sign. So let's graph y equals x sine x and see what happens. Oh, I like writing thick like this. It looks like the Khan Academy guy, you know? That's how he writes with a thick pencil. So y equals x sine x. Right? Doesn't he draws with thick crayons? He's my hero, so that's why I'm trying to be like him. So, so I'm going to use a cool graphing calculator. I'm going to go to my website, and on my website, where's my website? Come on. Everything was going so smoothly for a while. Where's my mouse? Your mouse. There we go. Let's try to click on that. On my website, I have a link. Some of you have used this before, I think. Desmos, if you guys used Desmos before, this thing, there's a link to it. It's a very cool online graphing calculator because it's really fast and it shows you all kinds of cool stuff. And so I'm going to type in y equals x sine. You could go to functions, x sine x, and that looks kind of like that. Okay? Now, that's kind of cool, but let's find some other cool things about this. If I go to y equals x, and if I also type in y equals negative x, and I'm going to zoom out quite a bit. What is that? Oh, zoom out again. Isn't that cool? Okay. So what is that y equals x and y equals negative x doing to my sine function?
It's like the range.
It's letting the range. So the range, right? What Gabrielle said, the range is kind of getting controlled by the y equals x function, right? Okay? And over here it's positive y equals x and y equals negative x because sine goes from positive to negative, right? And when you get to calculus, you'll learn about something called the squeeze theorem, and you're trying to prove that this is always in between these two things, but you don't have to worry about that. But But just so you know, so this is one type of trig function that I could do. And look, does the period, if I click on this point, that's 5 pi over 2. This is 3 pi over 2. This point over here is 9 pi over 2. Does the period appear to change as I move from here to here? No, the period doesn't change, right? It's just the amplitude that is controlled kind of by that y equals x, y equals negative x. Yes, Emily?
So if you were going to model with the spring, you would start with a larger amplitude?
Yeah, we're going to do one in a second.
Just go the other way?
Yeah, a good one. So it's hard to get, so how do I make it go down instead? Anyone know of a function that kind of looks like it would squish it down? Remember from last year? An inverse exponential function is going to make it do that, okay? So if I change this to, watch, if I change this to y equals y equals, and I'm not exactly sure why we throw a 3 in there, which makes it go fast, because you'll be able to see it better. Y equals e, you just go into the alphabet, okay? E raised to, you go back here, you could just, this is really cool, you don't have to hit that, all those weird stuff. Negative x, okay? Y equals e to the negative x, and over here I'm going to put e raised to the, raised to the negative x, and over here I'm going to put negative e raised to the negative x. I'm going to get rid of this x over here, okay? And then if I zoom in a whole lot, okay, how do I get rid of these points? Boom, boom, boom. And if I zoom in, in, okay, okay, then you get your damped, your squished down.
Wait, so which ones are which colors?
So this is y equals e to the negative x. This is y equals negative e to the negative x. And you can see again that it's kind of squishing down that sine function as you go. Why what? Why does it go to 4? I don't know. You could change that because I. Why?
3 in. Why is it?
Those are radians on that axis. Okay, so that's 2 radians, 4 radians. So this would be a little less than right. So it's almost one complete cycle would be here, right? 2 pi. Is that in terms of pi? 2 pi. I'm not sure what this up and down. It should just take. Is that radians or is that pi radians? I'm not sure. Okay, but in any case, you can see again that if I click on this point, pi over 6. Oh, because we have a, yeah, it is, those are radians, okay, because we have a 3 in front, right? So the period of that function is, 2 pi over 3. So it's going pretty quick, okay? And then if I click on this point down here, it'll be another pi over 6 away from that one. How do I show that? Pi over 2? Or pi over 2, is that pi over 6? 2 pi over 3 away from there, and so on. So again, the period does not change. It just, the e to the x function just squishes it down. So you're just kind of playing with this. We're not going to, you don't want to have to graph that by hand or anything like that. Just so you know that that thing is being multiplied by kind of controls the amplitude of the trig function as you go. Okay, so those are kind of cool. When you get to calculus, those are really fun to take the derivative of and integrals and stuff like that. So you'll like that. You have to use like 3 different rules at the same time. It's kind of fun. All right, so that's it. Your homework is on my website. It is right here, and it is. Oh, also, here's the problem of the week if you're interested. Right there, it's on my website. I'm going to close that. And where did I go? Where'd my website go? Going back, leave page. That's not where I wanted to go. I had my homework somewhere, didn't I? It was, come on. Up! Forward. There it is. Pre-calc assignments, chapter 4. You can look it up, but it is right over here. Partial. Is this it? Here, right? Right there. Okay. And there you go. And like I said, the problem of the week's optional, but it's kind of a fun thing.
Okay, so it's
And
page